In section 7.4, we bring back into play the counting techniques that we saw in chapter 6. So it's called the use of counting techniques and probability. This is part 1. So a gentle reminder that the probability of an event is simply the number of ways that that event can occur over the number of sample points inside that sample space. So again, the number of ways that E can occur over the number in the sample space. So we're going to start off with example 1. It says an unbiased coin is tossed 5 times. So we're going to toss a coin 5 times. 5 times, and we're doing a coin. What's the probability that the coin will land tails exactly 3 times? So part A is asking me for the probability of 3 tails. The probability that it lands tails 3 times. Well, we need the sample space first, and you'll see that as I work through these that I always go for the sample space first, because to me that's the more difficult challenge, is to solidify how big that event is. So what we're looking for is the number in the sample space. Well, we're tossing a coin 5 times. We know that when I go toss it the first time, there are 2 outcomes, a head or a tail, 2 for the second, 2 for the third, and so forth. So we know the number in the sample space is 2 to the 5th, or 32. So there are 32 ways that we can rearrange things when we talk about heads and tails. We want to know specifically 3 tails. Now, what we're really asking is amongst those 5 tosses, I could have the tails in these spots. I could have it in this spot, not this spot, not this spot, but this spot. So what we're really asking is the number of ways we can rearrange a T amongst those 5 spots. So that's the combination of 5, choose 3. So amongst the 5 positions, we want 3 of them to be our specified answer of T. That's all over the 32. So again, what we're looking at is the number of ways to rearrange a T amongst those 5 positions when we're tossing the coin. So the combination of 5, choose 3 comes out to be 10 over the 32 in the sample space, and that comes out to be 0.313. Part B of that problem says the probability of at most 3 times. So the probability that we get tails at most 3 times. Okay, that at most 3 times means that I can get no tails. So that would be no tails. Plus 1 tail, plus 2 tails, plus 3 tails. And that's what at most 3 tails means. Well, we already figured out this guy. We got to backtrack and figure out these guys. So to get no tails, there's only one way that's going to happen. That would be all heads. We know there's only one way for that. So you could do that as the combination of 5, choose 0. You'll get the same 1 out of that if you want to be consistent. Okay, to get 1 tail, I'm asking amongst those 5 positions, how many ways can I rearrange the T amongst those 5 positions? Well, it could be in the first position, or the second, or the third, or the fourth, or the fifth. That's a combination of 5, choose 1 over 32, and that should come out to be 5. To do 2 tails, we'll do the combination of 5, choose 2 over the 32. And again, that would be putting 2 tails in any one of these spots. And then we already know that the combination of 5, choose 3 over 32. And I apologize, I ran out of room. So I'm going to backtrack to the top of the board to finish off. Here. Okay, so that's going to be equal to, we have 1 out of 32. So the combination of 5, choose 1 is 5 out of 32. The combination of 5, choose 2 turns out to be 10 out of 32. And then finally, we already knew that the 5, choose 3 was 10 out of 32. So altogether, we have what, 26 out of 32? And if you want to make that into a decimal, that would be equivalent to 0.813. So if you're tossing that coin 5 times, the probability that you get at most 3 tails is 81%. So pretty high. And then part C says, what if we're going to get tails on the first and last toss? So what they're saying is that this one's a tail, this one's a tail, but nothing else is. So aren't these all, well, no, they don't care about the other ones. We know the first and the last have to be tails. They're not dictating these guys. So what we're saying is that there's one choice for the first spot, one choice for the last spot, but the other spots can be either a head or a tail. They're only dictating the first is a tail and the last is a tail. So that gives me what, 8 out of 32, which is a fourth or 0.25. So notice I switched how I was counting to do that one. Okay, the next example deals with the cards. This time, instead of dealing one card, we're going to take a look at 2 cards, which is why we need those counting techniques. Now, when you have a deck of cards and you're shuffling out or dealing out more than one card, the order that you're dealing in usually does not matter. You don't care that you get the ace first or last as long as you get the ace. So the order doesn't matter. So example 2. 2 cards are selected at random without replacement from a well-shuffled deck of 52 playing cards. Find the probability of the given event. The very first thing we want to do is find the probability that we get up here. We're going to do the bottom number first. So the denominator is going to be the combination of the 52 cards. We're picking 2 of them. That's my 2 cards that I'm picking. And that comes out to be 1326. We'll use that number a lot. That's why I know that one. Okay, well, now how about getting a pair? Well, what does a pair mean? What a pair means, so a pair means 2 of the same. So, for instance, we could go for a pair of 5s. Well, how many ways are there to get a pair of 5s? Well, I could have the 5 of hearts, the 5 of diamonds. I could have the 5 of clubs, the 5 of diamonds. I could have the 5 of spades, the 5 of diamonds, and so forth. So what we're going to do to figure that part of it out is figure the combination of the 4 cards that make up the 5s. We need to pick 2 of them. So that's the number of ways of picking a pair of 5s. Okay, they're very good with that, I hope. So the problem is we can't just have a pair of 5s. It could be a pair of aces or a pair of jacks or a pair of 3s. So there are 13 different pairs you could have of numbers. So the 13 is accounting for the different pair of numbers that you have. The 4 choose 2 is the number of ways of picking the pair amongst the 4 cards that would make up a pair. So 4 of the same number, and there are 13 different numbers. So the combination of 4 choose 2 comes out to be 6. So this is 6 times 13, or 78 out of 1326. Which is a decimal is 0.0588. Part B on that problem says 2 black cards are drawn. So now we're looking at the probability of 2 black cards. So the denominator is still going to be the combination of 52, choose 2, picking 2 out of the 52, order doesn't matter. But now we need the black cards. Well, there are 26 black cards in the deck, and we need 2 of those. So I don't have to do this multiplying by 13 because I don't care whether or not those black cards are the same number or 2 different numbers or even the same suit. So I could have a 3 of spades and a 4 of clubs, and it would fit what we're looking for. So the combination of 26 choose 2 is 325 over the 13, 26, and that comes out to be 0.245.